We have seen that we can use L'Hopital's rule when we have the indeterminate form 0 over 0 and infinity over infinity. In this video, I'd like to do these two limits, which are actually in the format of the indeterminate forms infinity times 0 and infinity minus infinity. Looking at this first example, the limit is x approaches 0 from the right-hand side of x times the natural log of x. Well, x is going to 0, so that's a 0. When x goes to 0, the natural log of x approaches its asymptote going to minus infinity, so generally in the format of an infinity times a 0. Well, to use L'Hopital's rule, what I'd like to do is rewrite this so that it actually looks like one of these. And so what I'm going to do is say, hey, multiplying x is the same thing as dividing by 1 over x. And if I look at this, the top is now going towards minus infinity while the bottom is going to positive infinity, the indeterminate form, and infinity over an infinity. I can apply L'Hopital's rule to this. The limit as x approaches 0 from the right-hand side. Take the derivative of the top, 1 over x. Take the derivative of the bottom, minus 1 over x squared. Let's simplify this. 1 over x times minus x squared over 1. And I get the limit as x approaches 0 from the right-hand side of minus x. Well, as x approaches 0 from the right-hand side, minus x goes to 0. And so the limit is x times the natural log of x, the limit of x times the natural log of x as x tends to 0 from the right-hand side is 0. All right, moving on to my second example. I have the limit as x approaches 0 from the right-hand side of 1 over sine x minus 2x plus 1 all over x. Well, as x approaches 0 from the right-hand side, sine of x here on the bottom is going to 0, making this whole fraction go towards infinity. This is a rational function with a vertical asymptote at 0, because 0 is a 0 of the bottom that doesn't cancel out anywhere. So this is in that format of an infinity minus an infinity. Well, let's just do some algebra before we do anything else. And then I'll rewrite part of this limit so that I can use L'Hopital's. And again, my goal is to turn one of these into one of the indeterminate forms that L'Hopital's directly applies to. So 1 over sine x minus, well, let's just go on and split this fraction up, do the division, maybe make it look a little easier. Okay, so now I have 3 terms to deal with. I'm going to rewrite this on a second board. The limit as x approaches 0 from the right-hand side of 1 over sine x minus 1 over x minus 2. I swapped the order of some terms here because I'm taking a limit as x approaches 0 from the right-hand side, and I'm worried about what this pair of things is doing, but as x approaches 0 from the right-hand side, the limit of minus 2 is minus 2. So I'm going to go on and evaluate that part and just let it sit out front. All right, let's find a common denominator here. So my goal here is to find a common denominator and add my fractions. Well, that common denominator would be x sine x, meaning that this first term I would have had to multiply top and bottom by x, and this second term I'd have to multiply top and bottom by sine x. And in looking at this, if I substitute a 0 into the bottom, I would get a 0. And if I substitute a 0 into the top, I get a 0. This is the indeterminate form, 0 over 0. I can use L'Hopital's rule. I still have my minus 2 from the part I had already evaluated. But now I can take a derivative of the top, 1 minus cosine x, and on the bottom I have to use the product rule. X times the sine of x, x times the cosine of x, taking the derivative, plus sine of x times 1. All right, so I try to evaluate this. On top I get 1 minus 1 is 0, and on the bottom I have 0 plus 0. This is still the form 0 over 0. I'm going to apply L'Hopital's rule one more time. All right, well here that goes away because the derivative of a constant is 0, and I end up with sine x on top. And on the bottom, I have to use the product rule here, so the first times the derivative of the second, plus the second times the derivative of the first, and then plus the derivative of that part is just cosine. So far I have minus 2 plus, still taking a limit as x approaches 0 from the right-hand side, of now sine x all over. And on the bottom of this fraction down at the bottom, I have a minus x times sine x plus 2 cosine of x. So now, minus 2 plus, on the top if I try to evaluate I get 0. On the bottom I get 2 minus 0. And so I have a limit of minus 2. All right, one important thing that happened here. The original limit I had was in the format infinity minus infinity. And my final answer is minus 2, which tells me that I can't look at something that says infinity minus infinity and say, well, it's 0, because I'm subtracting two infinite quantities. It tells me that sometimes if I subtract two infinite quantities, I might get something other than 0. And that's really cool, because it turns out infinities are pretty complicated. And this is why in these indeterminate forms, we always have to use L'Hopital's rule or some other meaning, and we can't just guess an answer.